Module 3, Lesson 3, Simpson's 3-8 rule. For this module, we will be covering basic numerical integration technique under Newton-Cotes integration formula, which is the Simpson's 3-8 rule, and the multiple application Simpson's 3-8 rule, and apply that on a given sample problem. The basic concept of an integral of a function is determining the area under your respective given curve. This particular estimate can only be done if your integral function has a lower limit value a, which is equivalent to x0, and an upper limit value b, which is equivalent to x1. The Newton-Cotes formulas are the most common numerical integration schemes that are used to estimate the integral of any given complicated function, the concept of which is to replace or transform this complicated function or tabulated data with an approximating polynomial function that is now very easy to integrate. This fn of x is an nth-order interpolating function used for estimating the integral of your given complicated function. Under the Simpson's 3-8 rule, the third-order interpolating polynomial function is used to estimate your integral value, fitting 4 discrete points onto your given cubic function, which is normally given either using Newton's interpolating polynomial third order or a third-order Lagrange interpolating polynomial function. This is the graphical depiction of a 1/3 rule against a 3/8 rule. Note that on a 1/3 rule, you subdivide the limit into 2 equal segments due to the fact that you are evaluating or estimating the area of your given function using a parabola. Therefore, you require 3 points on your respective function. Whereas for a particular Simpson's 3-8 rule as seen on the right-hand side, you need to subdivide your respective limit a to b into 3 equal segments to generate 4 distinct points in order to fit that onto a cubic polynomial function and estimate the area under this cubic function. When we integrate then this simple cubic interpolating function, it can be now simplified as b minus a multiplied to fx0 plus 3fx1 plus 3fx2 plus fx3 all over 8. However, since this technique requires a minimum of 3 segments in order to interpolate a cubic function, then its equally spaced formula for step size would then be equivalent to 3h is equal to b minus a. If we then replace b minus a with your 3h, then the formula can now be simplified as 3h over 8. Much like our trapezoidal rule and our 1/3 rule, our h or step size is multiplied this time by a factor of 3 over 8. And then we ended up with a sequence for your given particular pattern for your functions that are involved in your interpolation estimate, whereby the first and the last function is multiplied by 1 and all functions in between now multiplied by 3 times. However, as we've seen on the previous techniques, one particular cubic function usually is not enough to estimate accurately your integral value. Hence, we often apply what you call multiple application of the technique. Much like our trapezoidal rule and our 1/3 rule, multiple application Simpson's 3-8 rule can be improved by dividing your integral interval from a to b, or the lower limit all the way to the upper limit, into a number of 3 segment width, depending on how many cubic function you prefer to use. In which case, our equally spaced segments would now be equivalent to this formula, whereby h is the equal spacing, while n becomes the number of segments that are multiples of 3, with b being your upper limit value and a being your lower limit value. For a multiple Simpson's application 3/8 rule, then, the formula now becomes like this. We eventually end up adding composite of cubic integral functions until we ended up with the last cubic function. The first cubic function has a limit from x0 to x3. Then the next cubic function would have a limit from x3 to x6, all the way to your nth cubic function. If we then substitute then the integral estimates that we have for each cubic function, we would then end up with this respective formula. Note that each cubic function has a factor of 3h over 8. Therefore, we could factor it out and end up simplifying your given functions to be like this, whereby your h or step size is still multiplied by a factor of 2 over 8. And the pattern of your function now becomes the first function and the last function is multiplied by 1. Then all other functions are multiplied 3 times. However, all functions that are multiples of 3 are considered to be adjacent, therefore are multiplied twice. Or it can be generally written as this given formula. Note that this particular multiple application 3/8 rule can only be applied for segments which are multiples of 3, since each particular cubic polynomial function requires 3 segments. Let's try and apply that given technique onto this given problem, whereby we're asked to apply Simpson's 3/8 rule at a minimum of 3 segments. On a minimum of 3 segments, therefore, your step size would then be computed like this with a value of 0.2667. We then estimate the important values of x needed on our integral estimate, starting from your lower limit value x0, which is 0, all the way to your upper limit value, 0.8. In which case, the important values of x are as follows: x0, which is 0, x1, which is 0.2667, x2, which is 0.5333, and x3, which is 0.8. Substituting now these important values of x onto your respective function, much like what we did under trapezoidal rule and Simpson's 1/3 rule, we ended up with the following functions for fx0 to be 0.2, for fx1 to be 1.4329, for fx2 to be 3.4871, and for fx3 to be 0.232. Substituting it then onto our integral approximate formula, we'd end up with 3h, which is 3 times 0.2667 over 8, multiplied by our sequence of our function, wherein we multiply the first function once, which is 0.2, plus multiply all functions in between 3 times, which is 3 times 1.4329, plus 3 times 3.4871, and finally multiply the last function once, and then add 0.232. Hence, giving us now a summation for our function value equal to 15.192. Evaluating then our integral value would end up with an integral estimate for 3 segment to be 1.5194. Note that we applied that the same number of segments onto your trapezoidal rule, and we ended up with a respective integral estimate value equal to 1.3698. And we already know that the actual integral value should have been 1.6405, showing us that when applying Simpson's 3/8 rule at 3 segments, this particular estimate would be better than your trapezoidal rule, since a 3/8 rule still uses a curved cubic function as compared to a straight line used by your respective trapezoidal rule. However, using 3 segments, a minimum of 3 segments, is not enough to accurately estimate our integral value. So we then applied multiple applications Simpson's 3/8 rule using the next possible segment, which is 6 segments. Under 6 segments, our step size would then be computed like this with a value of 0.1333. Substituting this step size onto your important values of x, starting from the lower limit value of xo equal to 0, we end up with x1 having 0.133, and x2 of 0.2667, and x3 of 0.4, and x4 of 0.5333, an x5 of 0.6667, and an x6 of 0.8, all the way to your upper limit value. We then substitute these important values of x onto your function in order to fit them using your cubic function. Hence, your fxo would simply be 0.2, your fx1 to be 1.3102, your fx2 to be 1.4329, your fx3 to be 2.456, your fx4 to be 3.4871, your fx5 to be 2.8745, and finally your fx6 to be 0.232. Applying then our Simpson's 3/8 rule pattern onto your given function, you'd eventually end up with this respective solution, whereby you end up with 3 times h, which is 0.133 all over 8, multiplied with our respective pattern of function, and thus giving us a summation equal to 32.6581 with an integral estimate of 1.6325 for 6 segments. Note that we applied 6 segments using trapezoidal rule, and we ended up with a value of 1.5698, showing us that again, 3/8 rule turns out to be more accurate than your 3/8 rule, whereas your Simpson's 1/3 rule turns out to have a value at n equal to 6 equal to 1.6367. Against our actual integral value, you will see that among all 3 techniques now, your 1/3 rule still is the most accurate among all 3 integral approximate techniques. Likewise, you could tabulate a summary of the result, much like your trapezoidal rule, your 1/3 rule, and this time for your Simpson's 3/8 rule, to be like this. The Simpson's 1/3 rule is usually a method of preference because it attains a 3rd order accuracy with 3 points rather than 4 points required for the 3/8 version. However, the Simpson's 3/8 rule has a utility in tandem with the Simpson's 1/3 rule when the required number of segments is often odd and upon which neither technique is then applicable, much like if your n number of segments is equal to 5. Your 5 segment cannot be applied for Simpson's 1/3 rule alone, nor can you apply Simpson's 3/8 rule for a segment n equal to 5. Therefore, you could use the 2 technique in tandem in order to estimate a more accurate integral value as compared to your trapezoidal rule, which is the only technique applicable for n equal to 5. If we then apply that 1/3 rule and 3/8 rule tandem on a particular segment of 5 onto our given particular example, then we could evaluate the first 2 segments using the 1/3 rule and the remaining 3 segments using 3/8 rule, and then compositely add their integral estimates in order to estimate the value from A to B. If we then apply that onto our given particular function at n equal to 5, the spacing or the step size for your 5 segment would simply be this solution with a value of 0.16. If we then establish the important values of x needed on your integral estimate, you'd end up with an initial x0 value of 0, which is your lower limit, plus x1, which is 0.16, plus x2, which is 0.32, plus x3, which is 0.48, plus x4, which is 0.64, and finally, all the way to x5, your upper limit value, which is equal to 0.8. Substituting these important values of x onto your given function gives us an fx0 equal to 0.2, an fx1 equal to 1.2969, an fx2 equal to 1.7434, an fx3 equal to 3.186, an fx4 equal to 3.1819, and an fx5 equal to 0.232, upon which we'd end up with an integral estimate solution for the first 2 segments using the 1/3 rule, and added that compositely on your integral estimate using the 3/8 rule. Upon doing so, your 1/3 rule integral estimate would then be equivalent to h over 3, which is in this case 0.16 over 3, multiplied by our pattern of function, which is multiply the first function once, which is 0.2, multiply the next function 4 times, which is 4 times 1.2969 and multiply your next function once, which is 1.3474, giving us a summation equal to 7.131 and an integral estimate for the first two segments to be equal to 0.3803 square units. We then estimate the remaining last three segments using the Simpson's three-eighth rule, giving us now a pattern of this solution, which is 3 times your h, which is 0.16 over 8, multiplied by the first function this time, which is 1.7434, plus 3 times the next function, which is 3.186, plus 3 times the next function, which is 3.189, all the way to your last function, which is 0.232, giving us a summation of 21.0791 and an integral estimate equal to 1.2648 square units. Note that when we compositely add their integral value, the total integral estimate from A to B now, using the 1/3 and 3/8 rule tandem, is now estimated to be 1.6451 square units, which in this case would turn out to be more accurate than the one if you use a trapezoidal rule for n equal to 5. This ends Module 3, Lesson 3.